Hi, everyone, and thanks for joining. My name is Stefan Mabry, and I'm a PhD student at the University of North Dakota. Today, I'm going to talk to you about the project that sits at the intersection of machine learning, public health, and data explainability, and that is the explainable AI for diagnosis prediction from MEPS SDOH data. And we'll go into all those terms in a minute. So we're going to be looking at how different models can predict disease outcomes using only social determinants of health, which is SDOH. There are things like income, education, housing stability, and more importantly, they can be how they can be used to interpret those predictions using explainable AI or XAI. This work is kind of grounded in the 2021 MEPS dataset and explores whether or not we can make sense of the model's decisions using only the socioeconomic signals we get from the survey. And so the goal here is not just accuracy of the model, but also the interpretability, trust, and then ultimately clinical value. So the heart of this research is this: can we use AI to reveal how social factors like income, education, or access to care actually influence the diagnoses that patients receive? The formal research question is this: given a model trained to predict clinical diagnoses using social determinants of health, can explainable AI methods like SHAP or others help us understand which specific social factors contribute to each diagnosis prediction? That's the lens I'm working from, and the end goal is not just that predictive performance, but that insight of I want to be able to say, here's why the model flagged asthma or diabetes, and here's how social risk factors contributed to that call. So in other words, it's not just about building a powerful model; it's about making its logic visible to the end user. So that's where the explainable AI comes in. I'm using various explainable methods to unpack the model's behavior on the surface. To surface what the top contributors are for each condition. And I know that most of you don't have a clinical background, so I'll explain a few important terms. A diagnosis is a clinical determination about what condition a patient is experiencing, like asthma, diabetes, or depression. Clinicians choose from over 68,000 standardized ICD-10 codes to document these conditions. Some of them get oddly specific. Like I like the code V91.07XD, which is a burn that you receive due to water skis being on fire. And there's a whole bunch of those fun ones in there if you search through them. So SDOH, or social determinants of health, refer to non-medical factors that shape health outcomes, things like income level, housing stability, access to nutritious food, reliable transportation, and education. These are upstream social forces that shape downstream clinical realities. And then XAI, or explainable AI, I actually don't like anyone else's definition of explainable AI, and arguably true explainable AI doesn't exist yet. But that said, my definition of explainable AI is the science and practice of designing AI systems that provide human interpretable justifications for their outputs, enabling trust, accountability, and improved decision making while maintaining predictive performance. So let's talk about what we mean by social determinants of health. These are the non-medical factors, as I mentioned earlier, that significantly influence health outcomes, so income, housing, education, social support. This wheel on the left breaks down all of those terms into 5 broad domains, and these end up being like a survey to patients that they fill out their answers for. And the domains that they have here are economic stability, education access and quality, healthcare access, the neighborhood environment that you're living in, and then the social and community context that you live in. I linked the source in my acknowledgement sections, and you'll see that at the end of the presentation. So on the right, you see some of the actual MEPS variables that we use to represent these domains. So for example, phone interaction frequency and how often someone sees others socially relate to social connectedness. Financial strain is captured through the ability to cover an unexpected expense. And then we even have some more subjective metrics, like whether or not a person feels isolated or satisfied with life. So these aren't traditional clinical features, but they reflect the day-to-day realities that shape a person's health sometimes more powerfully than medical care itself. And the variables you see on the right are the same ones you'll see throughout the presentation. There's a lot more of them that didn't show up in the results as prominently as the ones that you see here. So the data set that I'm using, MEPS, it means the Medical Expenditure Panel Survey. It's a large-scale, nationally represented data set maintained by the AHRQ. It was designed specifically for analyzing healthcare utilization, cost, and insurance trends across the United States. And it's widely used in health economics and policy research. From a research standpoint, it's a gold mine if you're looking to understand how healthcare happens in the real world. One of its biggest strengths, and why I chose it, is how deeply it captures the social determinants of health information. All those upstream social factors, but it's specifically in the 2021 data set that has that information. It doesn't carry over to the other years, and the survey goes up to 2022. It lags about 3 years. MEPS data is not perfect though. It uses a rotating panel structure, so it means that it follows patients for only 2 years, and then after that short window, it limits the ability to detect like long-term or chronic disease modeling. From this project, it means that I can't model like lifetime cost of care, but it still provides plenty of signal for predicting clinical diagnoses, which is where I focus this presentation. And I've linked the data set here, and then also in the results, or the acknowledgement section. So here's what the data looks like. It's a fixed width file, no commas, no headers, just positional data. Each column is defined by a character placement, and so the schema has to be read separately using column specs file that they provided, but I kind of made my own, and you'll see that in the next slide. It's messy, but it's highly structured, and so you have to have a parser that you have to build to be able to pull the information out of this. So to wiggle out some of those usable features, we have the data set processing. So this is a sample from the MEPS codebook, which is essentially that key that tells us how to decode the fixed width file. Each row here represents a single variable, the variable's name, where it starts, where it ends in the data set, and then what it means. And if you clicked on the link, it'll take you to like a more detailed explanation of what the variables are. So if you took like the ADHD ADDX variable, that's whether or not a child, specifically between the ages of 5 and 17, has ever been diagnosed with ADHD. And you'll find it, specifically in the characters between 445 and 447 of each record. There's over 1,400 of these positions, and I translated this on the left to the one in the middle, which is my specs file that I import using the code on the right. So we load the data from the CSV, we parse it apart, and then we standardize the diagnosis codes. So when I clean up the diagnosis codes, if a patient visits their appointment for diabetes and hasn't been ever seen in their life for cancer, then the value in the field would be NA, despite the fact that the patient's probably not having cancer. It's just that the clinician didn't evaluate that, so it's not included in the data. So that I translated all of those weird answers into true zeros or no's, because the patient has not been evaluated for cancer or diabetes or whatever. And then the yes is the true yes, is that a clinician said, yes, you have this disease. So how did I do this project? My methodology. So here's a quick walkthrough. I started with the 2021 MEPS data set using only those SDOH variables. So we're not using any of the clinical data, just self-reported socioeconomic and behavioral information parsed against the 23 separate diseases that I was able to detect in the file. And so there's 23 then separate data sets that I parse out of this, each of 28,000 records or so. In the data processing phase, I one-hot encode all the categorical features that are used, and then I use oversampling, like a random oversampling method, to deal with class imbalance, because some of the diagnoses had far fewer positive cases than others. And then I applied standardization to keep things reusable for like the neural network pipelines. From there, I trained 4 types of models for each condition. XGBoost, a neural network, a decision tree, and then an ensemble model that combines all 3 of those other models using majority voting. This gave me a good spread from the interpretable, everything from interpretable models to black box models. And then after training, I applied 6 different XAI techniques that are popular in the literature today. So there's SHAP, Lime, integrated gradients, saliency maps, permutation importance, and feature ablation. Each method reveals something different about how the model arrived at its decision, but then I normalized the output for each method so that we can compare them side by side. And I used a max value reporting normalization. So everything's scaled between 0 and 1 based off the max value that it reported. And then finally, I evaluated both the prediction and performance as well as the explanation quality, looking at how consistent and clinically plausible the explanations were across the models and methods. So here's a breakdown of the 4 model types that I used for the study. Each diagnosis was modeled independently using all 4 of these models. And the reason for that is because you can have these things called comorbidities where you've got multiple diseases simultaneously. So having one does not preclude you from having another disease, and it's often not related to those other diseases, except in specific circumstances. So the first model type is XGBoost, which is a gradient-boosted decision tree model. It's especially strong on structured data like what we get from the MEPS. It is often a top performer in the tabular ML tasks, and that holds true with this data set, as we'll see in a minute. The next was the neural network. This is just a basic feed-forward architecture with 3 hidden layers using ReLU activation and then dropout for regularization. It's more of a black box approach, so it's important to include this as a point of comparison between the different models. And then there's the decision tree, which is a much more simple and inherently interpretable model, and I trained it with the Gini impurity values. It gives us a clean decision paths, and then it tends to underperform on noisy and imbalanced data, which is unfortunately what happened with this data set. And then finally, I used an ensemble model that combines the predictions of the other 3 using majority voting. And so this often stabilizes performance across a variety of data sets. And as shown in the 3rd column of this, not every model, or not every XAI method works with every model. Some methods like integrated gradients and saliency maps are specific to neural networks, while others like SHAP and Lime are more broadly compatible. So once you had our models trained, the next step was then to apply the explainability techniques. And so these are the tools designed to give us some of those insights that we're looking for. There are 6 methods here. So for SHAP and Lime, these are the 2 most widely used techniques that I found. SHAP is based on cooperative game theory. It estimates how much each feature contributes to the prediction by considering all possible combinations. It's performancely intensive. And so as such, I had to limit the data that I fed to it into like a random sample of 100. But then to get apples and apples, I compared that same 100 records across all the different models, so that you can compare SHAP between the models. Then there's Lime, and so Lime builds a simple local model around a specific prediction to approximate the behavior in a small neighborhood. This ended up not working very well, as we'll see in a minute. Integrated gradients and saliency maps are specific to neural networks. They use gradients, but integrated gradients works across a path from baseline to input, while the saliency just looks at the raw gradients with respect to the input. These help visualize which parts of the input are most responsible for a decision. And then we have permutation importance and feature ablation. These two involve messing around with the input data, either by shuffling values or removing features and seeing how the prediction quality changes. They're model agnostic and fairly intuitive. The right column then tells us what methods work with which models. So, for example, gradient-based methods require differentiable architectures like neural nets. So results. Here's a snapshot of our model's performance and a high-level summary of what we got from the explainability techniques. So on the left, we have the top 10 performing models by F1 score. I didn't include the same diagnosis. So this is one per diagnosis. So bladder cancer, for example, all the models performed very well, including decision trees, but XGB just happened to be the best. So all these binary classifiers are trained to predict the specific conditions, and it's based solely on the SDOH inputs. Most of the best performing models were either XGBoost or the ensemble methods, with the F1 scores between 0.92 and 0.96 range. So note the precision is often near perfect. Recall is where we see more variation, especially for conditions like cervical or lung cancer. And then on the right, we averaged and normalized the results from all 6 XAI methods to get a sense for which SDOH variables were the most influential across the board. So for example, telephone interactions per week came out on top, and that might sound surprising, but in many models, it served as a proxy for social connectedness and isolation. Other important features include physical activity, financial resilience, subjective isolation, and then general life satisfaction. Variables that show up consistently across different conditions and explanation methods. So even though we're using non-clinical data, we're still getting useful interpretable signals that correlate with health outcomes. Interestingly, the month the survey was completed also appears on the top features list. But it's only for it's only predicted by permutation importance. So no other XAI method actually identified it as influential when I dug into the data a little bit more. This is likely an artifact of how permutation importance works, coupled with statistical anomaly in where small cohorts of positive cases, like in the cases of cancers, where they happen to complete the survey in the same month for whatever reason, and then that would skew the results. So let's walk through some key findings from this project. First, from a modeling perspective, XGBoost, neural networks, and ensemble models all showed strong predictive performance when using just the SDOH variables. That's a solid outcome, and it tells us that there's meaningful signal in the data even without clinical features. Second, when we look at the explainability, SHAP is the most consistent. It produces stable, interpretable attributions across most conditions. Lyme, on the other hand, was much more erratic and occasionally surfaced features that just didn't make sense clinically. But we did see some features like exercise and social contact that appeared repeatedly across both models and XAI methods, which is a good signal to see. And the reason for that is probably because things like if you get cancer, you might feel more socially isolated from other people who don't have cancer just because you're focused on your disease. And then exercise is the same thing. If you have cancer, you might not be getting a lot of exercise. So there's not necessarily a causal relationship. So that brings us to the interpretation challenges. So it's important to emphasize that attribution doesn't mean causation, just like I just mentioned. Just because a model uses a feature doesn't mean it's explaining why a disease occurs. Sometimes it's just latching onto patterns in the data set, especially if the data is unbalanced or sparse in certain areas. And finally, the broader implications. So XAI tools are great for surfacing what models are relying on for specific decisions, but it doesn't tell us the whole story. If we mistake correlation for causation, especially in clinical contexts, we miss we risk making bad decisions. So while these tools are useful, we need to approach their outputs with care. So let's talk about some limitations for the study. Now, first, we're working with a single year of data, 2021 MEPS. That means we don't have any type of longitudinal insight. All the information comes from patient self-reports in a survey format that naturally introduces like a recall bias and limits temporal depth. So the feature set was intentionally restricted to social determinants of health. That excludes variables like the clinical variables like labs. And so not all conditions are equally influenced by SDOH variables. Arthritis, for example, it may show a strong SDOH related patterns, or it may not show strong SDOH related patterns because of the condition's commonness across a diverse population. It might not be influenced by those conditions. And then third, the explainability methods themselves have limitations. Attribution is not explanation, and definitely is not causation. We saw some unusual signals in this data set as well, like when we ran the results, like showing the month of the survey was completed being important, for the permutation importance methodology. That's likely just a like noise or an artifact of how the method works. And then finally, external validity is still an open question. We don't yet know if these findings would generalize to like other populations or different time frames or actual clinical settings. And that's the work that needs to get tested in the future. As we look ahead, there's 4 big areas where this research could evolve. First, integrating clinical data. So right now we're only using the social determinants of health, but adding like lab results, diagnosis codes, treatment history could help us build the models that are both richer and more clinically relevant. This will also help us understand if patients are managing their disease well, and then have that be read off by social determinants of health, and maybe even predict the social determinants from the clinical data. So there's a lot of ways you can slice this to get more information out and like more rich results. So second, we need clinical validation. So we should be testing these models using real-world EHR data. EHR is the electronic health records that health systems run to keep track of all your health information. And then we should also have clinicians review the results to make sure that the predictions and explanations actually align with what providers consider useful and trustworthy. Third, we want to move towards like a causal inference or counterfactual methodologies. So tools like SHAP or like causal SHAP or directed acyclic graphs might be useful for helping us separate correlation from the true causal relationships, which is especially important in healthcare. And then finally, we're just scratching the surface with this like next generation of explainability. Instead of just showing feature importance, we could also explore case-based reasoning, contrastive explanations, interactive tools where clinicians can ask questions and get more tailored and context-aware responses. And so that's definitely where we need to go as a society to have these AIs be more trustworthy. So to wrap up, there's 4 major takeaways from this project. First, we found that social determinants of health alone can meaningfully predict disease, even without the clinical data. The models achieved reasonably strong performance across several conditions. Second, model performance varied, with XGBoost and ensemble approaches generally outperforming the neural networks and decision trees. Neural networks still perform very well. Decision trees showed consistently poor performance, which is good to see the explainability across that spectrum. And then third, explainability helped highlight some strengths and blind spots. So tools like SHAP and integrated gradients pointed to relevant social economics features, but they also exposed odd patterns like that month of the survey being completed appearing as important for that one XAI method. So that largely reflects that noise as opposed to true signal. And then finally, it's worth repeating, attribution is not explanation. So I feel like these XAI methods are mislabeled in that regard. So just because a feature is influential in a model doesn't mean it has a causal relationship to the outcome, or that's a clinically valid way to approach predicting an outcome. And so that's the key caution that we should be thinking about, when using these tools in real world clinical decision making settings. Before I wrap up, I just wanted to acknowledge these two key resources. The MEPS dataset linked here. This is the specific one that I used, actually, the 233. And that powered the entire analysis. And then the SDOH framework comes from Healthy People 2030, which outlines the core domains used throughout the study. Both are publicly available, and I've included the links here for anybody interested in exploring them. So this is normally where I'd ask some questions, or I get asked some questions by the audience. However, you can reach out to me on the next slide. This is my email address, and then the QR code reaches my LinkedIn page. And of course, you're welcome to visit me in Madison, Wisconsin. Thanks for attending this talk. Have a great day.